So we had just seen the properties of GCD and a procedure, the Euclid's procedure to compute the GCD of two integers, and also to compute the corresponding Bezout's coefficients, right? The extended Euclid's algorithm to do this. So are there any questions from that lecture? Okay, if not, then let's continue with the last theorem that we left with. So here is the statement of the theorem. So did anybody get to try this? So there are two directions, right? First is when D divides C, there exists a solution. Whenever there exists a solution, the GCD must divide C. So did anybody try, have any thoughts where to begin? So let's try the easy direction first. Okay? Let's suppose there is a solution, then the GCD must divide C. Solution xy, which means integer solution to ax plus by is equal to c. Then I want to show that the GCD of A and B must divide C. So we know that D is the GCD of A and B. This means that D has to divide A and B has to divide B. So this means how can we represent A and B in terms of D? If D divides A, then what can you say about A?
A is K1D for some K.
Yeah. So A is some A prime D and B is some B prime D for A prime B prime integers. So now suppose there is a solution. We know that AX plus BY is equal to C is true for some XY. So let's just substitute. This implies that D divides, right? Where D is the GCD of A. Okay, so this is one direction, the easy direction. Now the other way around, we want to say that if D or the GCD divides C, then we must demonstrate a solution XY. As a solution. So let's so when we say D divides C, you should immediately say that you can express C. So that's the some integer K. Now what if C is 0? That is your equation AX plus BY is equal to 0. Then this equation, integer equation, x equal to 0 and y equal to 0 is a solution. So now we have two other cases. One is C greater than 0 and other is when C is less than 0. We will only deal with C greater than 0. So whenever you have a solution to C greater than 0, you can just flip the equation, right? You can make it A times minus x plus B times.
We can just apply the Bezout's theorem and then multiply with appropriate constant integer that will give like D to C because D divides C.
Right. Yeah, that is what we just want to demonstrate that it is true. Right. So it's exactly what Bezout's theorem tells us. Right. So we know that there is U and a V such that AU plus BV is equal to GCD of A B. Right. For some U. That's what Bezout's identity tells us. Right. Now we want to find XY such that this is true from UV. That's not wrong. Now you can write C as K times D, which is So this is my x and this is my, sorry, this should be y. So this has a solution. Okay, so x equal to ku and y is equal to kb is a solution. Where u and b are the Bezout's coefficients of a and b with this is with the GC. Right. So this is actually a strong statement, right? Ideally, what we would have done is we would have plotted the graph and then tried whether there is a solution or not, or whether there is some point integer solution to this equation or not, or this line. Is there any point on this line or not? But now you just need to compute the GCD of A and B, and you have to check whether it divides C. That's all. So this is a really nice way to understand solutions to equations. So now naturally one can ask, what can we say about quadratic equations or higher degree equations? We'll try to see some of them. Okay, so yeah, this is a really simple application. I'm sure you would have tried this. Okay. So moving on. So whenever, so as a special case of this, you can think about the case when GCD of two numbers is exactly 1, right? So A and A, B and C, such that GCD of A comma B is 1. Right? So this tells us that AX, so the above observation tells us that AX plus BY is equal to 1, right? The usual equation that's quite famous, has integer solutions if and only if the GCD of A comma B is 1, right? And just to note that whenever two numbers have a GCD 1, we call those numbers relatively prime. So A and B are relatively. And some books call this co-prime. Okay, so this is important terminology. You'll see like very often in this course, even when you read general books, textbooks on number theory, you say that two integers are relatively prime or co-prime if their GCD is 1. Okay, so now this also gives a characterization for equations like Ax plus By equal to 1. And we'll use properties of co-prime numbers in cryptography now. That's what we'll see next week. Okay, another cool observation from this Bezout's theorem. One of them is this. Okay, it's very nice that linear Diophantine equations, integer solutions have a direct characterization. The next observation is the following. Let's think about C. Okay, let's say that C is an integer. So A, B, C are all integers. So unless otherwise specified, we are dealing with integers. So can you say that if C divides AB, then C divides A or C divides B? Is this true in general?
C has to be a prime.
Okay, so is there anything else other than prime numbers that have this property? I will give you an example, maybe. Okay, so we know
A and B are co-prime.
A and B are co-prime. Yeah, somewhere close. Maybe when A and B are also co-prime, but with something more general.
If C is co-prime to both.
Okay, what if C is co-prime to one of them?
Oh, okay, ma'am. Sorry. Then,
Ma'am, not
then-
necessarily, ma'am. A and B can be co-prime, and this need not be true.
Right, exactly. So when C is prime, this is definitely true, right? That's how we define prime numbers. So they are so we will see more about prime numbers today, but when we talk about prime numbers, we know that the only divisors are 1 and itself. So for any prime number, P divides A and P divides A, or AB, then P divides A or P divides A. But in general, this might not be true. For example, here is 1, right? 15 divides 210, but 15 does not divide 6 and 15 does not divide 35. So this is a counterexample of the statement. So this implication is not true. But as he said, it might be that even A and B are co-prime, but this still might not hold. So one condition in this holds is in the GCD of A and C is 1. Okay. So if GCD of A and C is 1, what can we say? The immediate conclusion that we can get.
C divides B.
Right. C divides B, right? Because from Bezout's theorem, we know that you can write ax plus cy equal to 1, and you can multiply on both sides by b. So bax plus bcy is equal to, right? And c divides ab, so c divides this thing, and c also divides this thing. So c has to divide. So this statement that when the GCD of AC is 1, so it's 1, C divides AB, C divides B. So this statement is sometimes called Gauss lemma. What's this? I mean, there are several lemmas to Gauss, and this is one. So it may not be the case that C is prime. There are other cases where this is true. That's what this demonstrates. Okay. So moving forward, we want to talk about prime numbers. Okay, so definitely prime numbers are one instance for which this statement is true. Numbers, this is true. P divides C. So whenever we use P, we, at least throughout this section, we will denote P to be a prime. Right, and N is usually referred is used to denote a composite number. So you say that N is composite if there exists an integer P divides C. So these are like general definitions. Now we want to understand prime numbers. So it's not difficult to see that if you define prime numbers to be those numbers whose factors are 1 and itself, then prime numbers certainly satisfy this. P divides AB and P divides
Ma'am, in the lemma you wrote above, it should only be C divides B, right?
Sorry. What? Yes. Okay. So C. So it should definitely divide one of the factors, is what I meant. It depends on the nomenclature of what you choose B to be or A to be, right?
Yes, ma'am. I mean, when we say GCD of A and C is 1,
Hmm.
then I mean, if C divides A, then C. I mean, then C will be forced to be 1, right?
Yeah, that is fine, right? Because A, B, C are integers and C
I
could
mean,
be
in
1.
that case, if C is 1, then C obviously divides B. I mean, 1 divides B also. So it will itself imply that C divides B only in either case. If we assume GCD of A and C is 1.
Okay, so you're saying that the most minimal way of saying this is avoid this.
Yes, ma'am.
Yeah, I just wrote it to say that it should divide one of the factors of the number on the right hand side. Yeah, that's what we meant. So you could, yeah. So what I meant is the way we chose it, we chose this to be A and this to be. For example, in this, right, you could choose 6 to be A and 35 to be B, or the other way around, right? It should divide one of them. That's what I meant.
Yes, ma'am.
So now we can actually make a more general statement of whatever we observed above. Suppose P is a prime number and P divides A1, A2 to AN. Right? So all of them are integers. Then can we prove a generalization of what we have for this case? This one, right? So can we say that P divides A1 or P divides A2? Is this true? Can someone say why this should or not be true? I put a question.
We could do an induction.
I think we could do an induction. Let's try. Huh. Yeah, someone was about to say something. Yeah, go ahead.
Yeah, P divides A1 or P divides A2, A3, AN.
Correct.
If
Yeah.
P divides A2, A3,
So let me just write down whatever he's saying. So we know that P divides A1 through AN. So now just from this observation, you can make this as your A and the rest of it as your B. So I know that P divides A1 or P divides the remaining product A2 to A. Right? Again, this is a prime, so I can make this A, the rest of it B. Right? So that will give me P divides A1 or P divides A2, P divides A3 to A. Right? So going forward, I will get, and in the nth step, it will be P divides AN minus 1 or P divides AN. Okay? So this is true even for, even on the right hand side is not just two integers, but for any product, if the number is prime, then yeah, this is true. Okay, these are like really basic, but we are going to build on this. So I just wanted to ensure that. Maybe you have seen this in other courses. So have you seen the proof of fundamental theorem of arithmetic in other courses? I don't know, I'm just asking.
No, ma'am.
Okay. But maybe you have all come across that statement in high school. So the next theorem that we are going to prove is that if you look at any integer, you might all remember, right? We did this prime factorization. We looked at an integer and then we'll put a box around it. And then you'll divide by 2, divide by 3, divide by 5, and so on. And then you try to find out the prime factorization of an integer. That's what we're going to do. So this is called the fundamental theorem of arithmetic. Oh, so by the way, most of the theorems that we are seeing today are like really fundamental in the sense that they were all discovered in 300 BC or something. It's all written in a Greek book by Euclid. So there are several proofs of all these statements in various ways. I mean, some of them use number theory. So whatever we are going to see, at least in this course, will be only number theory. But then there are other ways to prove the same statements. So for example, even for GCD, there are other algorithms. For several of the theorems that we'll see today, there are proofs by Euler. So Euclid was probably the first because he lived in that era. And then there are proofs by Euler. There are proofs by more recent mathematicians. So you could see several proofs in other courses, but here we'll only look at like really number theoretic proofs, nothing beyond what we know. Okay. So here is the statement. Every integer can be expressed uniquely as product of primes, and by uniquely we mean up to order. So 2 into 3 and 3 into 2 are the same. So we need to prove this, but is the statement clear? For example, 6 is 2 into 3. Similarly, we try 2 into 2. So on. Okay. So let's first try to prove the existence. So we know as a base case that 2 is prime, right? So that we'll take for granted. So first I need to prove two things, right? First that given any integer, there exists a prime factorization. And the other question I need to say is that this factorization is unique up to ordering. Right? You cannot find two different factorizations of 6. The only way in which you could do that, you could just like play around with the orders in which these factors are multiplied. Okay, so the proof is by strong induction. So let's go to a method hypothesis. So let's say that this is true for all numbers, okay, where k is between 1 and n. So now I want to talk about the case when k is equal to n. Right? So I want to find the prime factorization for n. And I know the prime factorization for all integers that are less than. Yeah, so mostly in these proofs, we won't talk about negative integers because whatever works for positive integers also works for negative integers. You can just play around with the proofs. And the factors won't be different, right? You can just add a minus sign to one of the factors and it is still different. So it's okay to do this. So what can we say about n? We know that n is an integer. So it's either prime or composite. So if it's prime, we are done, right? N is a prime number and that's its own factorization. 1 times n. So what if n is composite? What do you think we can do? So far, what is the property of composite numbers that we have seen? The only property.
And they can be written as product of smaller numbers. and then
Because
you
there
can
is
apply the induction hypothesis
right.
on them.
So just the fact that it is composite means that there is an integer a that is greater than 1 that divides n. Right? So which means n can be written as a times b, where a, b, c, c. Is this clear to everybody? I mean, it is nothing fancy. I'm not doing anything. Cool. Okay, so now a and b are numbers that are strictly less than n. So I can apply the inductive hypothesis, and I know that a1 has a prime factorization. Let's say p1, pj. So what is the prime factorization of n? 2 times. Okay, so now what is it that we are left to prove? Uniqueness, right? So let's try that. So suppose n is an integer for which we have two prime factorizations. One is p1, p2 to pj. It's the same as q1, q2 to pj, where these are like different factorizations. Right? The numbers of prime factors are could be different. They could be different factors themselves, and so on. Now, when we know that there is a composite number for which two different factorizations exist, maybe there are several composite numbers that have this property. Let's take the smallest of them. Okay, so n is the smallest number for which two different distinct factorizations exist. Okay. So what can I say from this equation? Given that these are all primes.
P1 divides 1 of Q1, Qi.
Right. So is that clear to everybody? That this factor divides one of these because these are all prime numbers. Right? And these are some bunch of factors on the left hand side and some bunch of factors on the right hand side. So we can definitely say that P1 divides Q1 through Qk. Now you use this generalization here. If it divides a bunch of prime factors, it should divide one of them. Right? So this implies P divides Qi for some I. So let's say that P divides, okay, P1, right? So let's say that P1 divides Q1. That I is 1. And I know that P1 and Q1 are both primes. So what can I say about P1 and Q1? One divides the other and they're both primes.
They have to be same.
They have to be the same, right? So P1 has to be equal to Q1. So the moment you get P1 is equal to Q1, now what can you say about this equation?
Now, as we had assumed it to be the smallest such number, therefore the rest of the expression also has to be identical.
Exactly. So these two things get cancelled. So you'll get that P2 to Pj is equal to Q2 to Qk. And you know that this product is strictly smaller than the original two products that we started with. Right? So this means that there is another integer. Right? There exists another integer. Integer smaller than n that has two distinct this is a combination. So this is how you prove a basic number theory statement. So it's a very simple theorem, some theorem that we have seen so many times in school. They've all done prime factorization, but this is how you prove it. So you prove the existence and the uniqueness separately, just using a function. But this is a really powerful theorem. So now the next observation is, so how many primes are there amongst integers? we know like 2, 3, 5, 7, 11, and so on. And when does this sequence terminate? That's the question. Okay, so have any of you seen the answer to this question or the proof? I mean, I don't know. You're doing lots of courses, so maybe because there are several proofs of this statement, and there are proofs by Euclid, proofs by Euler. I think there are some more recent proofs also. Several ways to prove this using harmonic series, this, that, continuous map, everything. Yeah. So, does anybody know the answer to this, or have you already seen it in different proofs?
Oh, yes, infinite. Like take off.
Okay.
Like if there are finite number of up till Pn, then product of all the Pi is then n, and then plus one. That is also prime to all of them. That is the prime number.
That is prime to all of them. So this
I mean,
factor P1 to Pn so on plus 1. Okay, so let's see what Vijay says. Is that right or wrong? Okay, so that's what we want to say. Okay. The others can keep thinking whether it's true or not. It seems true what he's saying, but whether it is true or not. So the proof that we are going to see, I think, is by Euclid. By the way, there are like several other proofs. I will try to put a link to this. Okay, so what do I want to say? The answer to this question is infinitely many. The answer he said is right, but the idea he said is incorrect. Let's see why. So how do you prove this? A statement like this, that there are infinitely many primes. Okay, so I want to give you like few minutes to attempt proof, like 2-3 minutes. You don't have to give me the proof, but just see how does one prove a statement like this. Something about sequence, and we will only, so you can try to think about it only in terms of what we have seen so far. Like, don't think anything beyond that. No harmonic series, no continuous map, nothing. So let's try to. So the proof that we are going to do here is due to Euclid. Some 300 BC, I think. I'm not mentioning the date because it's before Christ. So I think it's like really old. Okay. So what we want to show is there are infinitely many primes. So if you come to me with a finite list of prime numbers, I should be able to demonstrate to you a number that is outside the list that is prime. Is that clear to all of you? Okay. So let's try what design said. So what he says is, we know that 2 is prime. So let's try 2 plus 1, right? 3. But 3 is prime. So we can try 2 into 3 plus 1. So if we have a list, let us say that there are, okay, let me just try to formally write down what he said. Suppose there exists a finite list of primes. P1, P2, so on to PR. So one candidate that he's saying is consider the product P1 to PR plus 1. Why does somebody think about a candidate like that? So we know that 2 is prime, we know 3 is prime, we know 5 is prime, we know 7 is prime, and so on. So we are going to try to construct these primes using primes that we have already seen. So 2 times 3 plus 1, 7, which is also prime. 2 times 3 times 3 plus 1, 51. Is that prime? It's also prime. 2 times 3. So this is 211. This is prime. Okay, so one question you might ask is, how did I quickly say that 211 is prime? We will see that probably in the next lecture, right? So I'm just throwing you some big number like 1452739. Is it prime or not? Can you tell me immediately? Are there ways to detect this? So these things we will see. But you can trust me that 211 is prime, okay, because I've tried this example. So the next option is this one, which is 2, 3, 1, 1, which is prime. Okay. Okay. So now let's try. So, 13 plus 1. Okay. So can someone quickly say what that is?
30,031.
Okay, I'm going to give you the factorization for that. 59 times 50. Okay, don't ask me how I did this, because this is usually a proof that people have that is incorrect, to say that there are infinitely many primes. So do people see that this is incorrect? So just because 2, 3, 5, 7, 11, 13 was a list of primes, it is incorrect to say that the product of these primes plus 1 is a prime number. So this sequence might seem prime up to a certain length, and then suddenly we start getting composite. Is everybody convinced about this? Like whatever I said so far? If we went too fast or it took you time, just tell us. Okay. Yeah, about the fact that these numbers are prime, please believe me. Hope they are. Yeah. So this is a counter example to that. But it's actually true that this is somewhat taking us closer to the next prime number. Right? So let's consider this number n. Let's call this number n. And this is the number we are actually going to use to construct a prime that is outside this list. So remember that n need not be a prime. But the goal is to use n to construct PR plus 1. So let's see n. N I know is greater than 1, right? Because P1 to PR are primes. I mean, there should be at least 2, and we are adding 1 to it, so it's greater than 1. Okay. So now what can you say for any number that is greater than 1, which need not be a prime or non-prime? What is one thing you can immediately say?
If
Just
only the primes we have are P1 to PR, then P1 dot dot PR plus, I mean, product of P1 to R plus 1 will be prime. If only the primes we have are P1 to PR. That was the hypothesis. So the hypothesis yielding that contradiction. So the proof is valid, even without constructing anything as such from n.
so given any list of primes, the product of these plus 1 is not true. Is a prime is not true. You are saying that is wrong? I didn't get actually what you are trying to say.
No, if all the primes we have in the natural numbers are finite, which is P1 to PR, then a product of P1 to PR plus 1 is prime, because none of the prime divides this number. None of the prime Pi divides this number. So
But
in
then
that
you are already using an infinite list of numbers, right? I mean, that's not okay. I did not get. So how do you prove you are already beginning with an infinite list of primes?
No, I am beginning with a finite list of primes. I'm proving by contradiction. Like assume there is a finite list P1 to PR. That is all the primes we have in the natural number system, and we are just taking their product plus 1. Since none of those primes divides this product, so this has to be another prime number, which also belongs to the natural number. So this is a contradiction.
So you are saying that, so what you are saying is something different, right? So what I'm saying is, given any finite list of primes, this plus 1 is not prime. That is true. But what you are saying is you begin with a set of numbers that is the set of all primes, right? But you have to use, but aren't you inherently using that it is infinite?
No, I am assuming if it is finite, then the P1 to PR will contain all the prime numbers, and this is a finite set because I am assuming that the number of primes is finite. In that.
Okay.
So after that, taking the product P1 dot dot PR plus 1, this is not divisible by any of the PIs in the list of primes we have in the natural number system. And because our assumption was the finite, like we have at most finitely many primes, and we are taking all the primes, all those finitely many primes in the form of P1 dot dot PR.
Okay, okay. Yeah, yeah. So, but generally this thing is not true. Like for any
Yeah,
set of primes,
generally
yeah,
it
for any
won't be true.
subset of primes is not true. Yeah, yeah.
Because PR greater than any prime might divide this product P1 to PR plus
Yeah, yeah,
1.
that is true. That is true. Yeah, yeah. So what I wanted to say is it's generally in. So the moment you see a set of primes, it's very natural to think that the product of these primes plus one is a prime, but it is not true. That's what I wanted to stress. Yeah. So now, okay. So now the only thing, I mean, one thing we could say is that there is a prime factor for n. Right? I mean, this we just know from the fundamental theorem, and let this prime factor be. Okay. So now, what could you do? I just want to say that P is not one of them. Suppose P is one of the PIs, right? What would happen? So you have n. Let's divide n by P1, right? So the quotient would be P2 to PR, and the remainder would be 1, right? So if I divide n by Pi, the remainder I get is 1. Yeah, but n divided by P, the remainder you should get is 0 because P is a factor of n. Right? So P cannot be any of the PIs. So the one thing that this says is that the product of these numbers plus 1 need not be a prime given a finite, I mean, given a subset of primes. Yeah, maybe that's how I should say. Right? But you can actually construct a factor of it that is prime. So the factor of, there will be one prime factor of n that is not in this list. So for any finite set, you can do this. Okay, so this is one thing I wanted to say about infinitely many primes. Is this clear? Okay. So now we have seen like how many primes are there. We know that there are infinitely many primes. So now I want to ask, if I give you a number and ask you how many primes are there less than that number, then how many would you get? So this is about distribution of primes. Okay, so let's say x is some integer, and I'm going to assume that it is greater than 0. So it's a positive integer, plus. We'll denote by pi of x the number of primes between 1 and x, or between, let's say, 2 and x. Yeah, let's write 1 and x. So this is a really important function. It's called the prime count. So for example, if you look at pi of 10, right? How much is that?
Four.
So you know the 2, 3, 5, 7. These are the primes less than 10. Right? Similarly, pi is 12. Then 11 will also come into the picture, and 5. So when we know that there are infinitely many primes, what can we say about pi of x as x tends to infinity?
Goes to infinity.
So you may or may not have seen this. Actually, I'm going to state it and then. So what is the prime number theorem tells us? It tells us how many primes are roughly there given any x between 1 and x. Okay, so have you seen this? How large is that number? How large can that number be in terms of x? Okay, so if you haven't seen this, here is the answer. It's roughly x by log x. Okay, so So it's roughly that many primes. So this proof is really non-trivial, and maybe you might see in other courses, some advanced courses. It will require a lot of effort. But we are going to prove a really, really toned down bound on pi of x, which is very weak, but it will demonstrate something good, right? That given any x, I can actually count the number of primes that are less than x, right? Bound, a weak bound. So here is for in x greater than pi of x. Log x, right? Or maybe ln of x. So is the statement, I mean, is this notion clear to everybody what pi of x is? What we want to prove? So we want to prove a lower bound on pi of x in terms of x. Okay. So let's go. So this is again by Euclid.
Ma'am, we are only defining it for integral x's, right? I mean, for integer x's.
Yes. That's what I said. Yeah. So all of what we'll see in this course are about is only about integers. Maybe we'll see one or two things about reals later on, but definitely not. So whatever we are talking is about integers. But the statement should be clear to everybody. What is going on? Okay, so what do we know from this infinitely many primes? We know that P1 through Pn are n primes. Then a prime factor of P1 to Pn plus 1 is also prime. So from this, what can you say about the n plus 1th prime number? How large can it be?
It must be smaller than this.
Right? Maybe in some cases it's much smaller, but it will be at most this, because this is the next prime. This is one of the primes, right, that come after that. Now here is the claim. I want to bound how large Pn could be. So if I get a bound on Pn, then I can somehow massage it to get the bound on the number of primes, right, that are less than a given. So here is the claim. Someone said something. Yeah, this is a really, really weak bound, but I'm still going to write. So do any of you see how to prove this? Not be hard. So let's try for n equal to 1. That's true. In the inductive hypothesis, let's assume that this is true for all P1 to Pk. Move to the induction step. So what do I know about Pk plus 1? No?
No, it is less than or equal to P1 to Pk product plus 1.
So now I can just use inductive hypothesis. Plus 1. And then this is 1 plus 2 plus 1. Oops, I missed this. This is fine. Right. Okay. I think it's fine. Okay, so you get that this is less than or equal to 2 to the 2 to the n minus 1 for all n. Okay. Okay, so now from Pn being equals 2 to the 2 to the n minus 1 for all n, what can I say about the number of primes less than, so I want to talk about the number of primes less than or equal to 2 to the n minus 1. So how many primes are there between 1 and 2 to the 2 to n minus 1 right now from what we have seen? At least how many primes?
10 primes.
That is I of 2 to the 2 to the n minus 1 is at least 10. Is this clear to everybody? Otherwise we can go over this. Okay, so now we have this thing. So given any x, what can we say? Now I want to say that pi of x is at least log of x, right? So whenever I'm given an x, I can actually choose n such that the log of x is strictly less than 15 and greater than 15. And I know that for x greater than or equal to 2 to 2 to the n minus 1, pi of x is at least greater than or equal to 8. Right? And n right now is greater than or equal to x. But it's all base 2, and then with some more effort, you can actually remove like ln of x. So you have to play around with the relationship between base e, base. I will leave it to you. But is this idea clear? I mean, it's a very weak bound. I mean, as is there are like x by ln x many primes, but I'm just telling you that it's at least ln of x. It's a weak bound, but it's one way to demonstrate that there are like so many primes.
And so for x by log x, the strong
Mhm.
one is base e, but for this one it's base 2.
No, so you can actually massage this to get base e. Yeah, I just didn't do it. You can play around with e and x, like 1 by e and so on. Yeah, bit, and you can actually get it. Base. Okay. So now I want to go back to this question that I was saying. That if I give you a big number and ask you like whether it's prime or whether it's composite and so on. Suppose I give you a number and ask you to test whether this number is composite or not. Right? So what are ways you could do this? One thing is you can divide by all numbers from 1 to n, and you can definitely check, right, whether there is one integer that divides n. But is there something that you can do better, like not go up to n, but do some computation that is much less than going up to 1 through n? 1 through n is like brute force, right? Can you do anything better? Let's say that I say that n is a composite number. Then what can you say about, so because n is a composite number or any number, it has a prime factorization, so it should have a prime divisor. But what can you say about these prime divisors? Will they all be large or will they all be small? Is there anything that you can say?
it will be less than equal to root over n. Yes.
So you mean that all of them have to be less than or equal to root n?
Oh, no. No. So by 2, but that is very trivial.
Sorry.
But n by 2, like no anything, yeah. So if n is composite, like n by 2 prime.
Will all the prime divisors be larger than root n? Let's say n is a composite number. So the only thing that I know about n is n can be written as a times b right now, right? So can a be greater than root n and b be greater than root n?
No.
This is not possible, right? So we know that a is less than or equal to root n, or b is less than. One of them is definitely less than. Now what can you say? Now both we know cannot be greater than root n, and we know that one of them is less than or equal to root n. Right? What can you say about a or b? Will they both have to be prime? Should one of them be prime? Or what happens if none of them are prime? So we did not say that a b is a prime factorization, right? We just know that n can be written as a times b, where a and b are integers. So either a is prime or b is prime. We know that one of them is less than root n, right? Let's say that a is less than or equal to root n and b is greater than root n. So maybe a is prime. Right? If it is prime, then we know that this composite number n has a prime divisor that is less than root n. Okay? Suppose a is greater than root n. Oh, sorry. Suppose a is less than root n, but it's not prime. Okay? Then what can you say? But not prime. So from the fundamental theorem, we know that there is a prime divisor for a. Right? So let's call that D are used for GCDs. Q, right? Q is a prime divisor. A, because A has a prime factorization, and Q also divides N. So what does this say? If N is any composite number, then there exists a prime divisor less than or equal to. Was this not clear? So it should be clear, right? Both of these cannot be greater than square root n. If both of them are greater than square root n, then AB is greater than n. Right? But we know that AB is equal to n. So this is not possible. I know that one of them should be less than or equal to root n. So let us assume that A is less than or equal to root n. Now A can either be prime or it could be composite. If it is prime, then I know that there is a prime divisor of n that is less than square root n. And that is A. If it's not the case that A is not prime, but A is less than or equal to root n, then I know that since A is an integer, it has a prime factorization, right? And there will be a prime q in it that divides n. So in any case, given any composite number, there always exists a divisor that is prime and it's less than or equal to square root n. Is this clear?
Yes.
Yes, sir.
So now if I give you a number and ask you whether it is composite, you don't have to run from 1 to n and keep dividing, right? You just have to look at all primes less than square root n, and then you have to divide n by all primes less than square root n. Right? If all of them say no, then you know that n is prime. Now here is a slightly different. So these things are actually what people call algorithms, but I'm not using that term because you are familiar with algorithms. Right? So these are some standard algorithms that people use to decide whether a number is prime or whether it is composite. Right? So if all of them return no, you know that the number is composite. So you can actually code these in your favorite language. You will, when you do the algorithms course, you will see how to write a program for this and how long does this run for large n. So when n is 100, instead of running from 1 to 100 numbers, you're just going to look at only like 10, 10, right? Until square root. So now here is another question. So based on this observation, so this is a seemingly important. So suppose I list down all numbers up to 100. Okay? This way. And I ask you to write down a program that will return all primes that are less than 100. Right? You have to figure out what are the primes that are between 1 and 100. So how will you do this?
Yeah, zero Pareto chemistry.
Oh, so this you have seen in some other course?
Yeah, in Haskell. Yeah.
Oh, I see. Okay. Yeah, so that is what I want to say. If you've already seen it, then maybe this one. But for those who like want to refresh, it is based on this thing, right? So there'll definitely be one divisor that's prime divisor that's between 1 and 10. So you look at all prime numbers between 1 and 10 and keep striking off those numbers. So 2 is definitely prime, 3 is prime. And you look at all numbers that are divisible by 3, strike all of them out. 6, 9, 12. So on, and keep doing this. Like 4, all numbers divisible by 4, you will strike out. In the end, the things that remain will be prime. So I wanted to say that, but since you are ready. So I'm sure you all know how to write a program for this. Okay. So this is fairly what I wanted to say about prime numbers. So we will come back to prime numbers maybe in the next week when we talk about crypto. But one thing to like think about. So this is not something formal that I'm going to say, but we will formalize it in next week. Is that if I give you a number and if I give you, let's say, 2 primes, okay? I don't know if you have seen this before, but I'm just going to say this. Let's say I give you 2 primes, okay, PQ, right? And ask you to write a program that multiplies P and Q, right? And give me the product. So this is a very simple multiplication program. I'm sure you all will be able to write this. Okay? I mean, there are standard functions to do this in programming languages. So you can do this. So I'm going to give, let's say I have a computer A. I'm going to give these 2 prime numbers to A. And I want A to spit out the product for me, and which it will do in like a fraction of a second. And think of these primes as really, really large numbers, like some 300 digit or it's a 200 digit primes. It will take some amount of time, but definitely like few seconds, and then it will be answered. Now I have another computer B, to which I'm going to feed in this number n. Right? And the task for B is to figure out what the original 2 prime numbers are. So it has to output P and Q, which are the original 200 digit prime numbers, or even 100 digit prime numbers. So n is a composite number. This is fed into a B. Essentially, what you're asking is the prime factorization. What is the original 2 prime numbers that computer A multiplied to figure out n? And this is something, if you haven't seen this before, is very astonishing that we do not know how to do this in less time. When we mean less time, if P and Q are of the order like 100 digits or something, it will take lots of years, like some 300 years, to actually find the original 2 prime numbers. Right? So we do not know of any algorithm or any supercomputer that can actually perform better than that. So it's a hard problem in the sense that integer factorization is something we do not know how to do. When I say we do not know how to do, this method that we used in school, right? Draw boxes. So this is something we can do by hand for small numbers. But for large numbers, we really do not know how to do this. Right? While multiplication is something that is so easy, inverting the multiplication is very, very hard. And it is the basis of this hardness that people use in cryptography for security. So if we give you an integer and ask you to keep it secret, right? If you somehow massage it to be the product of two primes, right? Or if I give you two primes and ask you to keep these primes very safely, you will just multiply it and keep it to yourself. And only you will actually know what those into prime numbers are. Nobody else can figure out what those into prime numbers are. When I say nobody else can, right? In finite amount of time, like some reasonable amount of time, right? So 200 years is not reasonable if I give this to a computer. So this is what we will see in cryptography. But for this, to understand whatever I said now, I must build some math. That's what we will do in this lecture and the next. So, like, does this make any sense? I don't know, because I'm not even seeing you. I cannot figure out.
Yes, ma'am.
Yes. Have you seen this before in some other course? Yeah, if you've seen.
Factorization is probably same, but like, why is it important? That is not the same.
So factorization is hard is something you have an understanding of, like you know why people believe factorization is hard.
Yeah, I think.
Okay. Okay. Yeah. For those of you who are seeing this for the first time, it might be astonishing that there are problems we do not know computers can solve it. Okay. So to understand or see how to use all this in cryptography, I have to introduce what is called modular arithmetic. So we will only see like really basic modular arithmetic today, and in the next lecture we'll do some serious stuff with it. Okay. So let me. Yeah, I heard that you have seen some basic modular arithmetic, so let me just. So we are going to only look at integers again. We'll say that A is congruent to B modulo N. Right? This is written as A congruent to B mod N. Okay, so this is the notation. This is like some super important notation that you need to remember. If N divides A minus B. Okay, so otherwise we will say A is not congruent. An example, let's say is 3 is congruent. So for those of you who have all seen groups, right? So this might seem familiar. A is congruent to A. And so these are things you can check for yourself. Yeah, if you have seen this before, then these properties are called reflexive, symmetric, transitive, and so on. And congruence forms an equivalence relation. If you haven't seen it, it's perfectly fine. You don't have to know these diagrams. Okay. So now there are several ways to interpret this congruence. Like what do we mean when we say A is congruent to B mod N? Right? And the whole of this next lecture we actually see this. Okay. So what does it mean beyond N divides A minus B? Okay. So some basic stuff. I mean, all of what I'll say in the next 5 minutes will be basic. Okay. So let's say A and B are integers, and I fix an N. So when I mean A is congruent to B mod N, I also mean that n divides a minus b, right? So a minus b can be written as k times n. In other words, you can write a as k minus b. But what does it say about a and b when you divide them by n? So a individually, if I divide by n, and b individually, if I divide by n, what does this say?
They have the same remainders.
Right. So that is what I want to observe. That by this notation, a is congruent to b mod n. Right. This is the same as saying that a and b leave the same remainder when divided by n. Okay. Okay, so I actually want to see a proof of this. This is something that's super important. Yeah, this will come up again and again, like A is congruent to B mod n, and C is congruent to D mod n, and so on. You have to play around a lot with congruences, and we'll use this. It's very simple. I shouldn't do this, but I will do it. Just to get a practice how to work with congruence. So this by definition means that n divides A minus B. This means that I can write A minus B is Q times n. Let's use this question. Right? So now I know that A, if I divide by n, I'll get some Q1 n plus R1, and B will be some Q2 n plus R1. And R1 and R2 are both integers, they are less than n. One of them is greater than the other. Let's assume that R1 is greater than R2. So now what can you say? Like, how do you show that both the remainders need to be the same?
N divides R1 minus R2.
Right. Right. So you look at A minus B, then you can actually play around with A minus B, and you'll figure out that. So you look at the expression for A minus B from these two things. And yeah, by some series of arithmetic, you get this. In other words, n divides R1 minus R2, so it has to be the R1. So saying that two numbers are congruent to each other mod n is exactly the same as saying that these two numbers leave the same remainder when you divide by n. So this means that, let's say you have the set of all integers here, and you fix n in. So let's look at all those numbers. So whenever you take an integer and divide it by n, the possible remainders are 0, 1, 2, n minus 1. These are the n possible remainders. And you put them into bags. So you pick an integer k, divide k by n. This will leave a quotient q and some remainder r. Based on whichever bag, whichever remainder you get, you put this k in that bag r. So this is bag r. So these are all those that have remainder r. So remainder 0, remainder 1, and so on. So all these integers, so the entire set of integers can be divided right, into these bags. Right? So what is one natural question that you can ask right now? I know that any integer I can put into one of these bags. Right? So let's take two elements here, k1, k2, and add them. Will it go outside the bag? Right? It is possible. Will k1 plus k2 go to it? Or if I multiply k1 and k2, will this go to another bag? I'm sure you've seen this in groups. Right? Have you seen this? The multiplicative group modulo n.
Sure.
Yes, right? Okay. So this is something basic. Right? So you have A is congruent to n. That is A and B leave the same remainder. If I add any two elements, that will leave the same remainder and so on. So you can actually add anything to A and C and it will be fine. right? The remainders will still remain. In the sense that if n divides a minus b, n will also divide a plus c minus b plus c because the c's will get cancelled. Right? Similarly, if a is congruent to b, then AC is congruent to BC. So I can add C to an existing congruence. I can multiply C to an existing congruence. Now the question is, can I divide? Right? So in other words, if AC is congruent to BC, A is congruent to B. Is this true? That is, can I cancel C here? Right? I mean, I can add, I can multiply, so I should be able to cancel. Right? Divide throughout by C. Oh, by the way, I can subtract also. So can I divide? That's the question. Is this fine? So this was a question. Let's see.
If C is co-prime with N, we can cancel.
Okay. So in general, can you do this? The answer is no. That's what he's saying. So here is an example. Right? So 6 is 12. 6. Yeah, they leave remainder 0. So this is true. Both 12 and 6 when divided by 6. This means that 2 times 3 is congruent to 4 times 3 not 6. But we know that 2 is not congruent to 4 times 6. Because if you divide 2 by 6, you get remainder 2. And if you divide 4 by 6, you get remainder 4. Okay. So in general, this is not true. One question is there some special case in which this is true? And it turns out that if you can play around with the GCDs, then you can actually say that this is true. Okay, so that is completely. So when will AC congruent to BC model imply that A is congruent to B model? Right? So what is the condition that you require on A, B, C, and so on? Somebody just said the answer for others. So I'll probably stop here. But one question that we'll talk about the next time is, what can you say about this question? Right, so this thing is super important in cryptography. It's called modular exponentiation. So you're going to raise these A and B to powers, and then you're going to divide by n and see what the remainder is. And then what happens? What if you know relationships between A and B? When I mean congruence relationships, what can you say about congruence relationships between A power K and B power K? Right? Why do we need this? How to compute this? This is a really, really large number, right? So even if I know A and A is like some 100. So in the end, when we talk about crypto, all of these will be primes. So this will be some 100-digit prime number. So you can only imagine how large A power K will be. We need to be able to compute this really, really fast using a computer. Okay, so we'll see these things. Okay, but for now, I'll just stop. Are there any questions?
What more will we be covering in this course?
The entire course. Okay, let me just stop it.
Yeah.
Recording stopped.
So our plan is to do a couple of more lectures on number theory. So by the way, have you all seen Fermat's little theorem, Chinese remindering and all in other courses? And I'm not aware of what other courses you do. So that's why I'm asking.
No, ma'am.
Okay, so we will do some basic number theory, like more basic number theory or more advanced number theory. Like we'll see Fermat's little theorem, Euler's theorem, all that. And then finally we'll do this protocol called RSA, which is what we use today for crypto systems. So we'll do that. So that will be like another 2-3 lectures. We are planning to end with April. And so first week of May, we want to allow TAs to give you some refresher lectures or maybe tutorials. If you have any requests, then we want to entertain that. So officially, like lectures will end with April, right? End by April, and then 1 week you will get time to like discuss with TAs. I think TAs may hold some sessions, right, based on whatever you would like to revise or refresh, or maybe your questions, something like office hours on Zoom. And then we'll have your end semester on May 18th. So we are planning to end with number theory, but if you have any like serious requests, then we can entertain that. You know, like 1 week. But we'll most likely end with number theory. And I think officially, like the last lecture will be April 28th, and then TAs will have some sessions on May 3rd and 5th.
Will we have another assignment?
Yeah, so we are not entirely sure. Even if there is one, the deadline will be after the second semester exam.
Okay, ma'am.
So we might release one because for probability and number theory, we haven't given you an assignment, right? So we'll give you the assignment before the end semester exam so that you will get some practice. Like you should know, right, what kinds of questions you have.
Yes, ma'am.
So just for your preparation, I mean, we won't grade that before the end semester. You'll be allowed to submit it after your end semester, like all the end semester exams.
Okay, ma'am.
Okay. Yeah, if there are any other questions, then otherwise we can meet on Thursday.
Thank you, ma'am.